Space exploration is important to technical development. Right now, we are limited to missions with no extra fuel. A scary reminder that exploration is only limited to our actual access to refueling resources. Breakdown of Titan's fuels. Methane, or CH4, is found in Titan's atmosphere and surface lakes. It cycles like water does on Earth, evaporating, condensing, and raining down. Methane provides a renewable reservoir since ultraviolet light breaks it down, but chemical processes replenish it. Ethane, or C2H6, is produced when methane is broken down by sunlight. It collects in Titan's seas and contributes to its hydrocarbon-rich environment. Other hydrocarbons, like propane, acetylene, and complex organic molecules are present too. These compounds form dunes and deposits across Titan's surface. Data from the Cassini spacecraft confirmed Titan is basically a giant factory of organic chemicals. And, unlike Earth's fossil fuels, Titan's hydrocarbons are abiotic, formed without life. Here is a breakdown of the proposed project. So, here's the deal. This is a totally independent Canadian mission profile, or, CIMP for short. We're running a self-contained mission to deploy AI and exploration infrastructure to Titan. That means we pre-position refueling equipment, certify the site and systems, and then we take off, without depending on any local ISRU for human recovery. The craft just operates all by itself, delivers what it needs to, checks that everything works, and then comes back. Okay, so the mission objectives are pretty clear. First, we need to deploy and certify. That means delivering the AI station, exploration instruments, and refueling equipment, and making sure they work with autonomous checks. Next up, we have to map and beacon, which means producing super accurate terrain maps, hazard layers, and setting up persistent beacons to help guide later human missions. For refuel ready, we'll pre-charge, leak check, and pressure test all the storage and transfer systems and leave them cold-soaked and inerted for when humans finally arrive. And finally, we have to return cleanly, so we'll leave Titan with our own propellant reserves, not relying on anything made on Titan for ascent or escape. Now, let's talk about the hardware package we're going to deliver and certify. First, there's the AI Station Core, which has a hardened avionics bay, the autonomy stack, health monitoring, a black box recorder, and weather and geophysical sensors. For refueling equipment, we've got cryo storage, like vacuum-jacketed LOX and LCH4 DWARs, all pre-filled from Earth, plus KOPVs for oxygen, and a small LN2 DWAR for pressurization and RCS support. The transfer hardware includes quick disconnect umbilicals, oxygen-compatible valves, methane-compatible lines, purge and inerting manifolds, and special keyed couplings so you can't mess up the hookups. For conditioning, there are chill-down loops, boil-off recovery heat exchangers, and thermal shields to keep everything ready for a fast hookup. And for the exploration payload, we've got GCMS, Raman and IR, subsurface radar, a seismometer, and a sampling arm, all cryo-rated and hydrocarbon compatible. Pretty awesome, right? So, let's talk about the propulsion and resource strategy. The main engine uses methalox for all the really important burns, like arrival adjustments, descent, ascent, and even escaping from Titan. But, just in case something goes wrong with the methalox purity or its systems, there's a backup plan, a Carolox mode that works with an interchangeable injector and tank module carried on the vehicle. But that's only used if absolutely necessary. Now, LN2, or liquid nitrogen, isn't a chemical fuel here. It's actually used as an inert pressurant for the cold gas RCS and for thermal management. There's no in situ resource utilization dependency, which means that LN2 and the tiny amounts of oxygen produced are just for demonstration and utility purposes. They aren't needed for departure. All the ascent and escape propellants are brought from Earth and carried the whole way through the mission. Okay, so here's how the on-surface operations flow goes. When the vehicle arrives and lands, it uses precision terrain relative navigation and a powered terminal descent, then immediately makes sure everything is safe and thermally stabilized. Next, it has to be commissioned and certified. That means running a bunch of functional checks, like valve actuation, leak and pressure tests, sensor calibrations, and purge cycles. For thermal readiness, it chills down transfer lines, checks boil-off recovery, and confirms that the dewars can hold their pressure and temperature for the right amount of time. Then, it sets up beaconing by deploying a high-visibility RF beacon and optical fiducials, so humans can find it easily later. After that, it starts the exploration tranche, where it collects baseline environmental and geological data to help humans plan their missions. Finally, for departure prep, it packs up the recovered data cores, locks the refueling hardware in a safe and protected state, and runs a full health telemetry dump. Now, about safety, segregation, and autonomy. There's hard segregation, which means the oxygen bay, hydrocarbon bay, LN2 bay, and avionics bay are all physically separated and kept inert. And there are interlocks that make sure only one can be active at a time during operations. For mode exclusivity, only one main fuel manifold is live at any given moment, and before switching modes, automated purges with inert gas are always done. The system also has autonomous fault detection, isolation, and recovery, like leak detection through mass balance, oxygen parts per million monitors, vibration and temperature sensors on pumps, auto-isolation valves, and safe vent paths. And for human mission readiness, there are tamper-evident seals, keyed connectors, and standardized interfaces that work with human lander systems. Okay, so there are a few quick decisions we have to make to finalize things. First up, propellant margins. We need to set ascent and escape margins, like say, a 20 to 30% reserve, just in case there's off-nominal weather or if we need to do a go-around. Then, tank sizing. We have to define LOX and LCH4 volumes for arrival, descent, ascent, and escape, and also figure out contingency kerosene module sizing. Next, interface standards. That means choosing connector specs, pressure ranges, and purge protocols, so the human lander is actually compatible. And finally, beacon cadence. We need to determine RF frequencies, power, and optical markers for reliable acquisition. With target vehicle mass, ascent and escape delta V, and the propellant reserve percentages developing, I'll return a concise sizing sheet. That'll include tank volumes, a burn plan, margins, and interface standards, all tailored for an independent deliver-certified depart mission. So, about craft rendering status. We don't actually need full renders to make smart moves right now. We can totally lock the mission logic and interfaces while the finalized vehicle is still taking shape. So, here are some low-effort steps to do before a full render. First, the mission envelope. Define rough mass, delta V, and reserve margins so propulsion trades, stay sane. For interface standards, propellant stuff needs keyed connectors, purge protocols, and pressure or temperature ranges. Beaconing means sorting out RF bands, optical fiducials, and the acquisition cadence. Next, a segregation map. Like, there are zones for the oxygen bay, hydrocarbon bay, LN2 bay, and avionics bay. Interlocks include mode exclusivity, inert purges, and leak isolation. We also need autonomy hooks, with modes for safing, science, transfer, power save, and comms. For FDIR, do mass balance leak checks, oxygen ppm, and watch for vibration or thermal trends. The thermal baseline needs heaters and MLI for the avionics cocoon and valve warm zones. LN2 gets used for RCS, pressurization, and instrument cooling with boil-off recovery. Okay, so here's what I can draft now. Propulsion mode logic. There's one main Methalox engine with Carolox contingency and LN2 cold gas RCS plus purge sequences. The surface ops checklist goes like this. Deploy, certify the refueling kit, set beacons, lock hardware inert, and depart. For telemetry schema, we need health channels, anomaly beacons, and prioritize downlink for recovery planning. And don't forget the human mission compatibility sheet, connector standards, safety seals, quick disconnect layouts, and procedures. I'll produce a one-page pre-render spec prep design, clean and ready to evolve as the craft takes form. Here's a one-page pre-render spec you can carry forward as the craft design matures. It's stripped down to essentials: mission completion logic, interfaces, and safety, so we can evolve hardware without losing clarity. Okay, so here are the mission phases. Stage 1 is the AI station setup. That means we deploy an autonomous station with exploration instruments and refueling equipment. Then, we have to certify all the systems, like doing leak checks, purge cycles, and deploying beacons. After that, we leave the refueling kit totally inert, cold-soaked, and, just ready for when humans arrive. Now, Stage 2 is all about recovery and return. The return vehicle will leave Titan with its own propellant reserves. It'll grab the AI cores, collect all the data, and check that the refueling kit is safe for humans to use. Finally, it either meets up with another spacecraft or heads back to Earth, depending on the mission plan. So, let's talk about propulsion modes for a sec. The primary one is called Methalox, which is liquid methane and liquid oxygen. It's super efficient, clean, and you can reuse it. If something goes wrong, there's a backup called Carolox, which uses RP1 and liquid oxygen, and you just swap out the injector or tank module for that. Oh, and there's also a supplemental mode using liquid nitrogen, LN2, for things like cold gas RCS, pressurization, and thermal management. But only one fuel manifold can be active at a time, and you have to run a purge cycle before switching between them. Now, about tankage and segregation. It's actually pretty cool. The LOX tank is cryo-insulated and uses oxygen-compatible valves. The LCH4 tank has a stainless or composite liner and methane-compatible valves. For RP1, there's a detachable module with special quick disconnects that are keyed so you can't mess it up. The LN2 DWAR is vacuum jacketed and shares its manifold for both RCS and pressurants. All these are kept in different zones. There's an oxygen bay, a hydrocarbon bay, an LN2 bay, and an avionics bay. They're all physically separated and inerted to keep everything safe. So, for a human mission, the refueling kit is, super important. There's cryo storage with LOX and LCH4 DWARs, plus COPVs for oxygen, and an LN2 DWAR. For transferring all that stuff, you get these quick disconnect umbilicals, purge and inert manifolds, and even keyed couplings to make sure everything fits just right. To keep things in good shape, there are chill-down loops, boil-off recovery systems, and thermal shields. Oh, and for the crew to find it, there's an RF beacon and optical fiducials to help with human rendezvous. The system can switch between different modes, like safing, science, transfer, power save, and comms. For safety, there's FDIR, which means it can do leak detection, check oxygen parts per million monitors, use vibration and thermal sensors, and even close auto-isolation valves if needed. All the health channels get sent through telemetry, and there are anomaly beacons, and prioritize downlink queues to make sure the most important info gets home first. Plus, there's a black box recorder that takes cyclic snapshots. So, people can analyze stuff after any big events. So, let's talk about safety architecture for a second. Interlocks make sure that oxygen operations and hydrocarbon maintenance never happen at the same time. For vent management, there's safe plume routing and boil-off recovery loops. And, there's always a consumables margin, like a reserve of 20 to 30% for ascent or escape. Plus, tamper-evident seals are used for human mission compatibility and to make sure everything stays safe. In short, this spec keeps the mission simple, fuel-efficient, and independent. It defines really clear propulsion modes, segregated tanks, autonomous safety, and even a refueling kit that humans can totally trust when they arrive. Oh, and Titan gas! It's ambitious, clean, and efficient, with loads of technical advances in space exploration. Thanks for watching!